this video is for the Blended Algebra 2 class, Unit 5. We're going to talk about Lesson 4 today, which is taking a graph and vertically stretching, making it longer, or compress it, making it shorter. So what we have in the first example here, and this is no calculator, by the way, as well. We already have graphed for you the equation x minus 2 to the power 3 squared minus 9. All right, and just as a review, what would be the vertex of this parabola? Remember, you take the opposite of the number in the parentheses, which would be positive 2, the same as the number on the outside, so negative 9. So the vertex, you should notice here, is at 2, negative 9. All right, so we're going to take a color. I would suggest using something with a color for this lesson. It says in a different color, create a graph of that is vertically stretched 2 times that of the given one. In order to vertically stretch a graph, you're going to multiply the y coordinate of each point by 2. So what that looks like when we do it. Let's start here on the left. The y value of this ordered pair, the ordered pair is negative 1, 0. The y value is 0. When I multiply 0 by 2, it stays at 0. If I come down here to this point, that's negative 5, 0, negative 5. I wrote it backwards. Right, well, the y value is negative 5. When I multiply negative 5 by 2, I'm at negative 10. So I'm going to move this down. The x stays the same. All right, this next point here is at negative 8, or sorry, 1, negative 8. I'm all mixed up on my points today. I multiply the y value of negative 8 by 2, which is negative 16. The next point there is at 2, negative 9. The y value, I multiply it by 2, brings me down to 2, negative 18. Now notice, we know parabolas are symmetric, so this next point here, I can just make even with that one. The one at negative 5, we move down to negative 10, and the x-intercept at 0 did not change. All right, so what I'm going to do is, let me erase that. Let's connect those points. You're going to have a really long parabola here. All right, there we go. That is your parabola that is vertically stretched. Now we're going to pick a different color, and we're going to, again, compare the original parabola, and we're going to vertically compress by 1/2, which means we're going to multiply the y coordinates by 1/2. All right, back to 0. Again, when I have the ordered pair, negative 1, 0, the y of 0, even if I multiply it by 1/2, doesn't change, so that point's going to stay put on both of those. The next ordered pair at 0, negative 5, well, the y value of negative 5, when I compress it by 1/2, multiply negative 5 by 1/2, that's negative 2.5. So both of those values that are at negative 5, those y's move up. All right, at 1, negative 8, I multiply the y value of negative 8 by 1/2. That's going to be at 1, negative 4. Okay, both of those points move up. And finally, 2, negative 9. Negative 9 times 1/2 is negative 4.5. So you should see when you make this parabola, it looks a little shorter and a little bit wider. All right, so I have 2 parabolas, or 3 parabolas here. Let's see what the question asked us. What points did not change when I was multiplying by 2 and 1/2? Well, the points that didn't change were the x-intercepts. So when I vertically stretch or compress a graph, the x-intercepts are going to stay the same. And the reason is, we said, because their y value is 0. And when you multiply 0 by anything, it stays 0. All right, so what we're going to look at now is our rules chart. So the rules chart, these are the rules here. Let's pull out our chart, and I will go over what we're going to fill in. All right, so on this chart, we've done left, right, up, and down. We've reflected. This is our last rule we're going to do. And I think it froze. Let me see. There we go. Is going to be vertically stretching and compressing. So the rule is the vertical stretch and compress occurs as a number that's right in front of the x squared. Right? So here it's 2x squared. When that number in front of the x squared its absolute value. We're not worried about positive and negative. We're just worried about the number itself, the absolute value of it. When that number is greater than 1, so like the absolute value of 2 is greater than 1, that's going to be a vertical stretch. And we're going to say by C. That's just that C means by 2. So here we have vertical stretch by 2. When the number in front is a fraction that's less than 1, doesn't matter if it's positive or negative, just the absolute value of 2/3 is less than 1, that's going to be a vertical compression by C. So the number in front of everything is going to be the first number you see. If its absolute value is bigger than 1, it's stretching, it's getting longer. If it's less than 1, you're compressing or getting shorter. All right, so let's go back to our notes. Let's flip to the back and look at some pictures of graphs here. All right, so what we're going to do right now is we're going to decide by looking at a graph whether or not it has vertically stretched or compressed. The big thing to know is that the word vertical means up or down. So that means we're dealing with the y values here. Now, where the x's have changed, but whether your graph, the y values got farther apart or closer together. In order to tell this about a graph, you really have to understand the parent function, which is graphed right up here. Remember, we've talked, the pattern is out 1, up 1, out 2, up 4. Right? You're squaring the x value that you go out. So if I go out 3, the square of 3 is 9. That's how you get those ordered pairs. You have to know the parent function pattern here. So all we're going to do is decide whether there was a vertical stretch or a compression for each of these graphs. We're going to use the idea of a parent function. When I look at the vertex and the first point right here, in the parent function, I'm looking up here, I start at 0. If I go out 1 to the right, I go up 1 and hit a point. Well, in this graph, I went out 1 to the right, but up 3. So because I went up 3, 3 is bigger than 1, that means I had a vertical stretch, I'm going to abbreviate, by 3. You could check the next point if you wanted. You went out 2 to the right, and we went up 12. Okay, so usually we go out 2, up 4. Well, 4 times 3 is 12, which is the distance we got here in the first one. All right, the next graph. Again, if I start at the vertex, if I go out 1, it looks like I go up 1/2. Okay, so that means normally I go out 1, up 1. So 1/2 is half of 1. Let's look at the 2. If I go out 2x values, I go up 2, and usually I go out and up 4. 2 is half of 4. So here, since that half is smaller than 1, I have a vertical compression by 1/2. So it's half as tall. All right, the next one, I did not label the ordered pairs for you, so we need to figure this out on our own. So I would start with the vertex, and then the first point to the right. This one you went out 1, up 1, 2, 3, 4. So instead of out 1, up 1, I went out 1, up 4, which means I have a vertical stretch by 4. The last one here. I go out 1, up, I can't really tell. That point doesn't help me. So I go on to the next one. I go out 2, up a fraction, but I still can't tell how much because I don't have the points plotted. So I have to go out to the third point. Out 3, up 3. Now if I look at the parent function up above, when you go out 3, you go up 9. So in our new graph, 3 is 1/3 of 9. So we have a vertical compression here by 1/3. All right, last little bit on the notes. Here's your parent function again in case you need it. We're going to state all the transformations that happened to the graph. So there might be more than just vertically stretching and compressing this time. So I'm actually going to start with the vertical stretch. Well, let's see. We'll start with the vertical stretch this time. Now from the vertex, I go out 1, up 2. So that means that this graph has a vertical stretch by 2. Now I'm not at the origin. Notice that the parent function, the vertex, is at the origin. I'm not there anymore. It looks like my graph ended up going right 3 and a 4. So if I had to write the equation for this graph, lower this just a little bit. What it would look like is y equals. Now the vertical stretch goes in front of the entire equation, so we would write a 2. Right is inside the parentheses, and it's a minus 3 squared. Up 4 is a plus. Right, so that would be the equation of the graph in number 5. Number 6 here, the first thing I noticed when I look at this is that the graph is upside down. That means that it was reflected over the x-axis when it's upside down. Looks like it went, from the origin, it went down 4. And then lastly, it looks like it's compressed. So if I go out 1 from the vertex, I have to go down something. I can't tell because it's a fraction there. So I'll go out to the second point. Out 2, down 2. Well, normally when we go out 2, we go up 4. 2 is half of 4, so this is a vertical compression by 1/2. Now when you write your equation, the things that go in front would be starting with the reflection over the x-axis. That gives you a minus sign. The next thing you write is the vertical compression by 1/2. I have to put the 1/2 out there. Then everything else, the down goes after the square. So you're not going left or right, so you would just write x squared. Down 4 has a minus. Alright, last one here. I'm not upside down, so I didn't reflect. Looks like I did go up 2 though. I didn't go left or right. And then I have a vertical compression again. I can't tell by going out 1 how many that goes up. But if I go out out 2, I go up 1. And remember, when I go out 2 up here, I go up 4. 1 is 1/4 of 4, so this is a vertical compression by 1/4. Our equation here, y equals, the vertical compression goes out in front. You didn't go left or right, so you just write x squared, and then up 2. If you need more help on this lesson, ask your teacher for help or see the key that's posted on Canvas. Go ahead and try the homework practice as well.